Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. I want you to take a minute and think about all the devices that you have connected to the internet right now. You have some type of computer, most likely a smartphone, a connected fridge maybe, a Nest thermostat, and maybe more, right? That's a lot of devices. In the early days of the internet, let's say around 1979, Internet Protocol version 4 or IPv4 was created, and it allowed for 32-bit IP addresses, which allows for 4 billion IP addresses. But if everybody has so many devices that are connected, that's just not going to work today, and definitely not going into the future. Internet Protocol version 6 or IPv6 changed things to 128-bit addresses, which resulted in 2 to the 128th power. That is a ton of IP addresses. So many that I'm not even going to try to pronounce it, and I'm just going to go with 340 undecillion addresses. Now, IPv6 has been on the future roadmap since the IETF published the draft standard in 1995, but it hasn't had much wide-scale rollout until starting around 2017, where it started being deployed by some companies and internet service providers. Let's go ahead and dive into more about IPv6 addresses. If you've seen an IP address up to this point, it's most likely been an IPv4 address where you have 4 decimal points like 192.168.1.5. With IPv6 addresses, they're formatted completely different, and it might seem a little weird at first. You can see on the screen here that IPv6 doesn't use decimals and instead uses a colon to separate 16-bit groups. Now, in an IPv6 address, each 16-bit group is called a quartet or a hextet, with each hexadecimal number going from 0000 to FFFF. Don't worry if the letters are uppercase or lowercase, although developers are going to tell you that it should be lowercase. Now, a few special notes are that you can't have all zeros or all Fs for the full address. And you'll always have 8 groups of 4 hexadecimal characters in the full address. The first 64 bits are reserved for the network prefix used for routing, which is further broken down into a routing prefix and a subnet ID. The second 64 bits are the user portion called the interface ID. Now, I know you're probably sitting there thinking that IPv6 addresses are pretty long in general, but there are some shortcuts in order to make it easier to write these out and to use these addresses. The first thing that you can do is drop the leading zeros from any group. You can see on the screen here what that looks like. We have all the leading zeros in red, and then in green is what it ends up looking like. Next, you can use 2 colons to represent 1 or more consecutive groups with a value of 0. Keep in mind that you can only do this shortening once though, like you see on the top group of addresses. If you had a group of zeros not consecutive with the 2 groups, like on the bottom of the screen, you couldn't also eliminate that extra group. They have to be consecutive, so right in a row. Just like with IPv4, we can use CIDR notation for the IPv6 network prefix. When an IPv6 device first boots up, it's going to have a link local address, which is similar to an APIPA address for IPv4 addresses. That's the IP that starts with 169. That address is a unicast address that's specific to that system. The link local address starts with FE80::, and it's a /10 CIDR notation, which must have 54 0 bits. That really means that the link local address is a /64 CIDR notation. The second half of the link local address, or the interface ID, is generated in one of the following 2 ways. The first possible way is that most consumer operating systems will randomly generate a 64-bit number. The second way in older operating systems is that they might use the device's MAC address to create the last 64 bits, which is also called an extended unique identifier, or EUI-64. If you don't need an internet connection for the system, then this is the only address that you're going to need. Keep in mind that if you see this address being used, that there aren't any DHCP servers. Global unicast addresses are routable public addresses needed for internet connectivity and is also a unicast address. These addresses are managed in a similar way to IPv4 addresses, where IANA manages these and delegates the distribution to the 5 regional internet registries. We have ARN, the American Registry for Internet Numbers for North America, the Caribbean, and North Atlantic Islands. We have RIPE Network Coordination Center, or RIPE NCC, for Europe, the the Middle East, and Central Asia. We have Asia Pacific Network Information Center, or APNIC, for the Asia and Pacific regions. We have Latin American and Caribbean Internet Address Registry, or LACNIC, for Central and South America and parts of the Caribbean. And we have African Network Information Center, or AFRINIC, for Africa. IPv6 doesn't use broadcast messages like IPv4, and instead it uses multicast messages while limiting some of the scope where messages are sent to specific groups of systems. Now, I've given you a few examples on the screen here, but it might be worth Googling the full list just so you can see it. For example, a system can send out a multicast message to FF02::2, and the first two means the scope is the local network segment, and the last two indicates the messages for the group of routers within that scope. If you change that first two to an 8, then that means the scope is the entire organization. Imagine that you're trying to access a YouTube video. The best delivery of that video streaming is going to come from the server that's closest to your location, but you only know the IPv6 address of the YouTube website. That's where anycast addresses are useful. Anycast addresses are a single IP address shared by multiple hosts where the goal is to have the router's direct traffic to the nearest server to the client. The most common use of anycast addresses is with something called the Content Delivery Network, or a CDN, that caches information around the world to give the best experience in all locations. Just like in our YouTube example, we want that CDN to direct us behind the scenes to the closest server to us with that anycast address. IPv6, just like IPv4, needs a protocol to help determine MAC addresses or layer 2 addresses of devices to use with their IP address. IPv4 uses ARP, and in IPv6, we use the Neighbor Discovery Protocol, or NDP. Now, NDP uses ICMP version 6 to do a lot of the functions like ARP does. There are 5 control message types encapsulated into a single packet for NDP. We have neighbor solicitation, neighbor advertisement, we have router solicitation, router advertisement, and redirection. Neighbor solicitation messages are used to request a MAC address, tell that system their own MAC address, and to make sure the system is still reachable. If a system doesn't know the MAC address and needs to send a neighbor solicitation packet, it'll send it to the solicited node multicast address shown on the screen. That's the address where the last 6 hex digits are the corresponding unicast address. If the system just needs to make sure that the system is reachable, it can send the message directly via unicast. Now, if a host receives a neighbor solicitation message, the host adds the MAC address of the sending system to its neighbor discovery cache, which is like the ARP cache. It will also send a neighbor advertisement in response to the neighbor solicitation so that the sending system can store the unknown MAC address into its own neighbor discovery cache. Basically, the whole purpose of the protocol. Those are systems on a network use router solicitation messages to find the routers on a network. These messages are sent to the all routers multicast address. Router advertisements hold important information about available routers on the network, which include the MAC and the local link addresses of the router and how hosts can get a global unicast address. These can even be configured to give out DNS information if you want. Routers will frequently announce their presence on the network, but router advertisements are also sent in response to router solicitation messages. These are sent to the all nodes multicast address, or in specific circumstances, to a unicast address. Redirect packets enable routers to inform hosts if there's a better router for them to use to reach a destination. Obviously, for this to work, you would need more than one router. Now that we know a lot about IPv6, let's talk about some of the common implementations that you might see. Stateless Address Auto-Configuration, or SLAAC, is a technology that enables network clients to determine their own addresses. It relies on the neighbor discovery process used in NDP. When a system generates their local address, they also send out a neighbor solicitation message to make sure that it's not taken. Systems can generate their global address once they get the address prefix from router advertisement messages that are sent by routers. If a host is joining a network, they can send out a router solicitation message to request a fresh advertisement. Then the host can use the network ID to generate their address and then send out a neighbor solicitation message to the new address to make sure that it's available. DHCP implementations for IPv6 can be different than IPv4, and it works in one of 2 ways. Stateful, which works just like IPv4, where in this case the server assigns 128-bit addresses and keeps track of everything that's been assigned. Stateless is the other type of implementation for DHCP version 6, and it still provides clients with information like DNS server locations, but it allows clients to use SLAAC to pick their own addresses. If you want to see your IPv6 address configurations, the standard command line tool ipconfig on Windows, IP address on Linux, or ifconfig on macOS will show you that information. Routers typically will have something called a default route, which means that's where they're going to send traffic when they don't have a direct path for it. As you climb up the ladder of routers that manage the internet, called Tier 1 routers, they don't have any default route, and these make up the default free zone, or DFZ. Fortunately, there's an idea of something called aggregation for network routes, and the idea is that each level of router only needs a small subset of information compared to that next level. This reduces what a router actually has to store by a whole lot. This concept becomes even more important with IPv6 because the number of devices that exist and that are going to exist is insane. It's entirely possible to run both IPv4 and IPv6 at the same time. A lot of organizations are actually doing that right now, and then when they actually are going to transition over, it's going to be relatively smooth. Some technologies or implementations, especially across the web, might not be ready for the transition yet or have backwards compatibility. And if that's the case, you have a few different options. One option is to use IPv4 to IPv6 tunnels, which involves using a special tunneling client to encapsulate IPv4 traffic inside of IPv6 tunnels to get an IPv6 enabled router. You also have IPv6 in IPv4, which is an IPv4 tunneling protocol that can go through IPv4 NAT, also called NAT traversal. Since setting IPv6 tunnels in general can be challenging, you can use something called a tunnel broker to create the tunnel and handle logins for you using either the Tunnel Setup Protocol, TSP, or Tunnel Information and Control Protocol, TIC. Overlay tunnels is another option which enables two IPv6 networks to connect over IPv4 connections like the internet. Basically, IPv4 information gets added to IPv6 traffic for transport, and then it's stripped off at the receiving end. NAT64 is like this and adds bytes of IPv4 addresses to IPv6 to transport traffic, and then NAT64 gateways can handle the translation when it receives that traffic.